Hello and welcome to this next lecture on fundamentals of acoustics. We have been looking at waves on a string and we looked at the solution and we were trying to understand the solution in terms of phasors. So, I had a crank slider mechanism with a mass moving back and forth and tied to a spring of infinite length. We have seen this in the last class. I just want to add one more point, that suppose this crank starts off with an initial phase, initial position right here, okay. Then I can assign that same phase to the first point, okay. So, it will be e to the power j omega t plus j pi by 2, but this will get assigned to every point. Every point that comes next will have e to the power j omega t plus j pi by 2 minus kx minus jkx. So, the initial phase does not matter, it gets added to all the points, it is only the phase difference that matters. So, the phase difference between this point and this point is e to the power of minus jkx, okay, and that is due to the phase change over unit distance multiplied by the actual distance by which the second point is behind the first point. That is the delay in transferring the information, okay. Now, I said we will look at this in another manner, okay. So, let us say this is my time axis, this is my time and these are stations . And this direction is my space and these are stations, points where we monitor, okay. And suppose this starting point is the starting point over here, that x equal to 0, let us say, okay. And suppose this phasor happens to be horizontal to start with, okay, and this is delayed time, this is delta t behind, that is 2 delta t behind, this is 3 delta t behind, 4 delta t behind, okay. So, what happens is this phasor is rotating, right, this phasor is rotating. So, delta t later, let us say it rotates by 45 degrees or 22 and a half 45 degrees, let us say 45 degrees. At 2 delta t it rotates to 90 degrees, at 3 delta t to 135 degrees, at 4 delta t it is completely 180 degrees, okay. Now, there is a point to the right, there is a point to the right here, okay. Let us say a point delta x to the right, that will see the information little later. So, it is going to be, let us say 45 degrees behind. Now, this as time moves it becomes horizontal over here and it becomes 45 degrees over here, it becomes vertical over here and it becomes 135 over here and it becomes pi over here, okay. So, this is the phasor allotted to a point delta x to the right of the starting point. We take another point which is, let us say twice delta x, okay. Here this is going to be vertically down further behind, here it is going to be 45 degrees in this way, here it is going to be horizontal, okay. Here it is going to be 45 degrees this way, here it is going to be vertical 90 degrees, here it is going to be 135 degrees and so on, okay. So similarly this point will be further behind 3 delta x, okay. So if you move forward in time and forward in space, if you move forward in time and forward in space at the right speed, what you will find is you can find the same phasor description, okay. I have moved a little bit in time forward, a little bit in space to the right, and I find the same movement. I move a little further to the right and a little more in space, I again find the same description, okay. So this is how e to the power of j omega t minus kx looks like, okay. So the plus j omega t is rotating it's forward, minus j k x is rotating it backward, okay. So that a forward movement in time is matched by a forward movement in space such that this value remains the same. That is why this arrow is horizontal here, here and here, okay. So this is a forward travelling wave, or a right travelling wave. This minus over here ensures that, this minus ensures that, okay. So correspondingly e to the power of j omega t plus kx will be a left travelling wave. Left travelling wave, okay. So that is as far as this phasor description and the physical meaning of this solution, which is y of x comma t is equal to a tilde e to the power of j omega t minus kx plus b tilde e to the power of j omega t plus kx. I will put a tilde here to imply that it is complex, it is a complex expression, real and imaginary both, okay. Now we will solve a few problems. Now that we understand what is going on, okay, we understand physically what is going on with this term and this term, we will solve a few problems, okay. One of those is a forced, so first problem is a forced semi infinite string. So we have a semi infinite string, that means it extends from x equal to 0 to infinity, it is under tension T, okay, and this point is x equal to 0 and there is an applied force F tilde which is of the form F e to the power j omega t, okay. Now as I said before, this is a right travelling wave, and this is a left travelling wave. Okay. Now if I have an infinite string over here, and I start exciting or disturbing the string at x equal to 0, then a disturbance will continue moving on the string to the right forever, because it is infinite. Okay. So there is never a chance that something will come back. So there is never a chance that there is a left travelling wave. Okay. And so we are going to set b tilde to 0. In a more mathematical setting, this is called the Sommerfeld radiation condition, which we will see much later. Right now we are setting b to 0 using physical arguments. Okay. So now my solution has only one component, y tilde of x comma t is a tilde e to the power of j omega t minus kx. So I have one complex unknown, and so I need one complex boundary condition. Okay. So what is that now? So that condition has to be set up over here at x equal to 0. It has to be set up over here. So there what we have is a point with hardly any mass, okay, and it is subjected to a force F tilde, and there is tension from the string acting, okay, and the vertical component of the string is T del y del x, T del y tilde by del x. Okay. So now if del y del x is positive, this is positive, okay, this angle, then T del y del x is positive and the force is upward, that is physically also seen, force is upward. This is the physical picture, the mathematical picture. Similarly, if del y del x is negative, that means the string has this shape, the shape of the string is here, okay, then T del y del x is negative, okay, and physically you can imagine that the force is downward. Okay. So the sign is accounted for along with the physical picture. So what is the condition? What is the boundary condition at x equal to 0? Because the point has no mass, the sum of forces is equal to 0. Okay. It should be mass into acceleration, but it is a massless point, so it is 0. Okay. So what do we have? We have F tilde plus T del y tilde by del x at x equal to 0 is equal to 0. That is the condition. Okay. Now F tilde is capital F e to the power j omega t plus T the tension. Okay. Now from here the del y del x is a tilde minus j into k e to the power of j omega t minus kx, and at x equal to 0. So this is gone, this is gone, okay, and that is equal to 0. So if we cancel e to the power j omega t and a happens to be the unknown I am interested in, so what I have is f is equal to j k t a tilde, okay. It means a tilde is equal to f over j k t, okay. So a tilde is equal to f over j k t, which implies my final answer is y tilde x comma t is equal to f by j k t e to the power of j omega t minus k x, okay. So that is the answer. Now T is rho L C square, okay. So T is rho L C square, the tension T is rho L C square, and so we will keep it like that. So we will call it, we will take J on the top minus J F by K rho L C squared e to the power j omega t minus k x. Okay. Now here is where the cos sign issue comes in. Many are not comfortable with this, okay. I will most of the time leave it at this expression, okay. But if you are not comfortable, then you have to decide whether f was f cos omega t or the forcing was f sin omega t, okay. And if in your mind the forcing was f cos omega t, you have to take the real part of this solution, you will take the real part of the y tilde solution, and if you think the forcing was f sin omega t, you will take the imaginary part of the solution. So you get both in one shot, and it is much easier to take derivatives. That is the reason we choose this exponential notation, okay. Now this is what we call a steady state solution, okay, a steady state solution. What we mean by that is that if you have a string and you excite it and you start exciting it suddenly at time t equal to 0, okay, f tilde is equal to f e to the power j omega t, and you start exciting it at a certain time, then there is going to be a transient on that. There will be a transient that will propagate, okay, along with what you are forcing. So that transient is not accounted for in this, okay. We assume that the transient has died out. So even though there is no dissipative mechanism in the string, okay, we assume that the transient has died out, okay, let us say decayed, okay, transient has decayed, let us say, okay. It is very commonly done. If we actually include a dissipative mechanism mathematically, then the solution becomes difficult, okay. So we do not do that, but we assume that there is some damping mechanism, and so we remove the transient and we look at what happens due to the forcing alone. So that is called a steady state solution, okay. Now I will just show you that If I substitute let us see, if I substitute y as a e to the power of j omega t minus kx into the partial differential equation del 2y by del x square is equal to 1 over c square del 2y by del t square. Okay. If I substitute this in here, okay, and omega is my driving frequency, then what do I get? Double derivative on the left, a tilde minus jk whole squared, okay, e to the power of j, the phasor, is equal to 1 over c square, double derivative with time, j omega whole squared, a tilde e to the power j times this phasor. So, a can be removed, the phasor can be removed. So, what I get is k square is equal to omega square by c square. Omega is known to me, okay, so that my k is equal to plus or minus omega by c. So, what that means is, once I know my omega, once I know the driving omega, with what frequency the string is being driven, then the wave number is known to me. Okay. Omega directly gives me the wave number k. This is called the dispersion relation. This is one of the simplest dispersion relation. Dispersion relation relates omega to k. Okay. So, we were discussing elaborately about e to the power j omega t and minus j k delta x, but we never discussed how we arrive at k. Okay. This equation straight away gives you the relation between omega and k. Once you know omega, you can find out k. Okay. They are directly related. So, now let us look at the impedance. So, with respect to the spring mass damper, we discussed what is impedance or what is mechanical impedance. So, here also we will do the same. So, my y tilde x comma t is equal to minus j f by k rho l c squared e to the power j omega t minus k x. Okay. And impedance requires velocity information. So, we will do del y tilde by del t. So, I get a j omega minus j into j omega f by k rho l c square. I need the velocity at x equal to 0. Why? Because that is where my force is located. I need to find the mechanical impedance from the force location. So, I need to compute velocity at x equal to 0. Okay. So, that gives me e to the power of j omega t. Okay. So, this part is my v tilde. This part is my v tilde, if you recall, v tilde. So, this is v tilde e to the power of j omega t, and my forcing was f tilde, which is f e to the power of j omega t. So, I need to find f divided by v tilde. Okay. So, this v tilde further is equal to minus j and j go away. So, I get omega f by k, I will replace by omega by c rho l c square e to the power j omega t So, this omega goes with that omega, this C takes out 1 C. So, I have rho L C left. So, now F divided by, so the mechanical impedance is F divided by F by rho L C, which is equal to rho L C. Okay. Now, earlier we said that we could have mechanical impedance as a complex number, a real part times a j x, okay, and we said the real part indicates dissipative aspects of the system, the imaginary indicates the inertial and stiffness aspects. Okay. Now, here this rho L C is purely real. Okay. So, there is no imaginary part to the system and there is a dissipative part to the system. Okay. But at the starting we said that the string material has no dissipation. So, why is this impedance purely real? Okay. Now, one thing is that it is not only when the mechanical energy gets converted to thermal energy, okay, that is when dissipation is present, okay. But also if there is power being taken away, power contributed, okay, or taken away from the driver. Taken away from the driver. So, in this case when the forcing agent is forcing the string over here and then the displacement moves, okay, what the forcing agent sees that the power is being taken away by the string forever and nothing comes back, there is nothing coming back. Okay. So, on the average there is power being given to the string. Okay. And therefore, the impedance is real. Okay. So, the power now is going to be 1/2 f square r by magnitude of z m square, and in this case it is f square r, which is rho L C, okay. So, r is rho L C by twice magnitude rho L C squared. So, it is f square by 2 rho L C. This is the power dissipated, average power over one time period which is twice pi by omega. Okay. Now, there is no imaginary part to this system, okay, there is no imaginary part, and so this system does not demonstrate resonances, no resonances. Okay. Now let us look at another example, second example. Okay, example. What is this example? This is a forced finite, okay, fixed string. What do we mean? It is a finite string, okay. It has a certain length, it is under tension, it has a certain length, okay. It has a length L, let us say. So it is finite and it is fixed. Here it is fixed, on the right hand it is fixed, 0 displacement, okay. On the left here at x equal to 0, this is forced as before, okay. There is an f tilde, it is forced harmonically to this, okay. So now let me just give you a physical picture. When I start exciting the string over here, then waves are set forth, they go to the right. Here there is a discontinuity, the string is fixed. So what happens is there will be reflections from the string, I mean from the fixed point, and then the incident and the reflected, they will start interfering, okay. And the final response will be that due to a right travelling wave and a left travelling wave. And here also we are looking at the steady state, that means there could be transients which have died out due to an imaginary superposed dissipative mechanism which we do not introduce mathematically, okay. So now in this case you should see that my solution will have both components, a tilde e to the power of j omega t minus kx plus b tilde e to the power of j omega t plus kx. Okay. Now we have two unknowns, a tilde and b tilde. So we will need two boundary conditions, and as I said, initial conditions, their effect has gone to 0. That is what we mean by steady state. Okay. So now we start again. First condition, first boundary condition at x equal to 0 is the same thing, my f tilde plus t del y tilde by del x at x equal to 0 must be 0, the same condition as before, okay, which means what, f e to the power of j omega t, okay, plus t. Now del y tilde by del x is a tilde minus j k e to the power j omega t, and because as x is 0 I leave it out, then plus b tilde j k e to the power j omega t, x is 0, this is equal to 0. So this is one equation, and because e to the power j omega t is not 0, I will take it out, I will cancel it from every term. So what I now have is f plus t jk minus a tilde plus b tilde equal to 0. This is one equation. Okay. The next condition, the number 2 condition, is that at x equal to L, the displacement y x equal to L for all time is 0. Okay, it is fixed. It is fixed. So that gives me y tilde L comma t is equal to a tilde, I will write it slightly differently, minus j k L plus b tilde e to the power j k L. I will put the j omega t outside. Okay. Now this is equal to 0. Okay. So e to the power j omega t is not 0. So therefore this term must be 0. Therefore b tilde will be equal to minus a tilde e to the power minus 2 j k L. Okay. So right away let me tell you one thing, that the magnitude of b is equal to the magnitude of a. Okay. I just want you to remember this observation. We will use it later, or we will understand it later. Okay. Even though b tilde in its form is quite different, if I take the amplitude on the left and amplitude on the right, then they are equal. Okay. So as I said, we will see this later. Okay. Now we have both equations now, so we should be able to solve it. So let us see if I can substitute this information into this information. So we will call this number 2. So f plus t j k, okay, minus a tilde plus b I write as minus a tilde e to the power of minus 2 j k L equal to 0, or f minus t j k a tilde into 1 plus e to the power of minus 2 j k L equal to 0, or a tilde is equal to f by t j k into 1 plus e to the power of minus 2 j k L. So a is known. Once a is known, b is known, because from here then b tilde is equal to minus a tilde. So minus f by t j k 1 plus e to the power minus 2 j k L into e to the power of minus 2 j k L. Okay. So a is known, b is known. So my answer is known. I have the answer over here. Okay. I have the answer, but we will put it back into the expression and simplify. So let us put it back. If we put it back in here, what we get is y x comma t is equal to 8 f by t j k 1 plus e to the power of minus 2 j k L. Inside I have e to the power of minus j k x, then I have a minus for the b, then I have e to the power of minus 2 j k L, I have e to the power plus j k x, and I put e to the power j omega t outside. Okay. This is the same expression as this after I put in A and B. So now if I simplify this, I will take f by t j k, I will take e to the power of minus j k l outside, so that I have e to the power of j k l plus e to the power of minus j k l. In the numerator also I will take e to the power of minus j k l outside, so that I have e to the power of minus j k x minus L, okay, minus e to the power of minus plus jk plus jk x minus L, e to the power of j omega t. Okay. Here I have, here what do I have? I have e to the power minus j k l, and here I have e to the power plus j k l. So, e to the power of minus j k x remains, and here I have e to the power of minus j k l and e to the power minus j k l twice. So, this matches. Okay. So, what I have now here is this. I will rewrite this a little differently, just change of sign. Okay. F by T j k, I will cancel e to the power minus j k l, okay, and this I write as twice cos k l, and this I write as e to the power of j k l minus x minus e to the power of minus j k, okay, l minus x, just a convention issue, okay. And this we know is what? This is equal to f by T j k twice cos k l, okay, and this is twice j sin k into L minus x. Or if I take out the j and the j and the 2 and the 2, this is f by tk sin k l minus x by cos k l. Okay. So, that is the, yeah, so there is a time also here e to the power j omega t. Okay. So, that is the answer to my finite forced fixed string. Okay. I will close the lecture here, and we will continue looking at this expression and get some physical insights in the next class. Thank you.